Hey, welcome to the theory of static energy. This is video number 1 of about 6, I'm not sure yet. This theory will prove that we do not need to burn poisons in order to fuel our sacred economy. This is explained in a simple step-by-step manner so that anyone can understand this. You can understand this if you watch these videos. This will be big fun. There's no math involved in this theory. Now, you who are educated in these matters, please be patient through the rudimentary information. It will be worth your time. And just for a teaser, the dynamic force of gravity is how the kinetic energy of the universe behaves relative to any local environment within that universe. It's all about micro, macro, etc., etc. Okay, so now here's drawing number 1. We're out in space here. We're millions of miles away from anything else. There's no planets, no galaxies, no nothing anywhere near this. These are called thought experiments. We will imagine things in these thought experiments, but all the things we imagine will be things that are actually possible. I'm not going to have any thought experiments about things that can't be in the physical universe. So there's a spaceship out there. Somebody went into a little decompression chamber, opened a window, and shot this arrow out of the window of the spaceship. This arrow was going about 200 miles an hour when it left the arrow string, and because there's nothing else around, there's nothing acting on it, nothing pushing on it, nothing pulling on it, nothing bothering it, it's going to keep going the same velocity and the same direction until, 10 years later it runs into a galaxy or it runs into something that starts to pull it off course a little bit. But the main thing is there was a force that pushed on this thing one time, pushed it up to 200 miles an hour, and now it's going to stay at 200 miles an hour and keep going in the same direction until something else interferes with it. This is all rudimentary standard physics. This here is a rocket ship. This was shot from the same spaceship, and it was going 200 miles an hour when it left the launcher. The difference, of course, is that this thing is burning fuel. That fuel is creating a force pushing against the hull of this thing, and so it's not going to go the same velocity all the time like the arrow. It is going to constantly increase its velocity as a result of the constant force pushing on it. And it's the same thing. It will keep going in a straight line, and we're going to assume it's always burning the fuel at the same rate. It'll keep going the same velocity until something interferes with it. So this thing we're going to associate with the word force. This we're going to associate with the word energy. And the thing is that gravity, magnetism, weak force, strong force, etc., etc., they do not act like this. They do act like this. That's why I call gravity, magnetism, strong force, weak force, any self-existing permanent force in the universe is actually static energy. And if you understood the relationships, you'll know that that's actually true. Okay, here's the next drawing. See how rudimentary this stuff is? This is a train car sitting on a train track. Everything's flat, everything's level, everything's perfect. Good wheels, good ball bearings. This is a flat, level steel floor. This is a round steel ball. It's 6 feet high, weighs a couple thousand pounds. It can roll forward, it can roll back, it can just sit there, can bounce side to side a little bit, but it's being held within the car. Of course, here's a rocket ship burning fuel. Putting a force on this thing wants it to move forward. Right now we're imagining the brakes are on, so it's not going anywhere. It's just burning fuel. It's just vibrating, waiting to take off. Uh-oh. So here's number 2. And on this one, the brakes were released and this thing suddenly shot, just took off like a bullet. And what happened to this steel ball inside this car when that happened? Of course, it slammed into the back of this, right? It's just like if you're sitting in a car, somebody steps on the gas and it forces you to the back of your seat until it stops accelerating. The same thing happens here. But just keep in mind that you don't actually get slammed into the back of your seat. Your body just tries to stay where it is and the seat is pushing you forward. The same thing with this. The ball doesn't actually slam into the back of this. This thing slams into the ball. Now, there's a property that all things that are physical have where they do not want to change their velocity or their direction suddenly. That's the best way to put it. That's called inertia. Everything has inertia. We know what that is. So, yeah, if the velocity is 0, it doesn't want to move. Now, as long as this train continues to accelerate, to keep getting faster and faster and faster, this thing will feel that pull, pulling it toward the back of this. So that's that one. And now we have this situation. This thing accelerated up to 50 miles an hour, and now it's going steady. 50 miles an hour steady. It's not going faster. It's not going slower. And what's going on inside here, I don't know how this guy got in there. It doesn't matter. But now, as long as this isn't accelerating or decelerating, he can push that ball around inside here like it's not even moving. He can push it forward, he can push it backward. It'll just sit there because that's how inertia works. You only feel inertia when something is accelerating or something is decelerating. In other words, getting slower or faster. If it's going the same speed, no matter how fast that speed is, doesn't matter. You will not feel any inertia. This thing could be going 100 miles an hour. Long as it's going steady at 100 miles an hour, he can push this ball forward and backwards and it would not feel the inertia at all. Or 1,000 miles an hour, doesn't matter. Okay, now this was set up so that as soon as this ran out of fuel, say 10 minutes later, as soon as this ran out of fuel, the brakes automatically slam on this thing. So it ran out of fuel, they slammed the brakes on this, and what happens to this ball? Of course, it goes flying and bangs into the front of this thing with a great deal of force. Just like if you were in the front passenger seat of your car and your little friend driving was texting and then you hit a telephone pole. You go flying through the windshield and you get killed by science. Do not text and drive, kiddies. All right. So now we're expanding this idea a little bit. Here's a guy out in space again. He's this rocket ship is burning fuel. It's producing a constant force, which means it's going at a constantly increasing velocity. As long as that's happening, this guy is standing on a platform. I should have started out with that. Here's a guy standing on a planet. Here's a guy standing on a platform. We're going to assume this platform is so big that he cannot see this rocket ship underneath him. So the rocket ship's burning fuel, creating a constant force. This thing is producing a constantly increasing velocity. So what is this guy going to feel standing on this platform? He's going to feel exactly the same thing this guy feels. Just like that ball being slammed into the back of the train car, or you being pushed in the back of your seat when someone steps on the gas, as long as this thing is burning a constant force, it's producing a constantly increasing velocity, he's going to feel a force pushing him down on this floor. And it turns out that that force is very, very strongly related to the force of gravity that this guy feels. And I think that's all I have to say about that one. Trying to do this quick here so I don't waste people's time. Now, this is a way of understanding why things in this world fall at exactly the same rate. Out here in space, this guy is standing on this platform. He doesn't know there's a rocket ship there, so it feels just like gravity to him. Now, he's got a 10-pound bowling ball and a 10-ounce steel weight. If he lets go of these things, they are both going to fall at exactly the same speed. Because what's really happening here, he lets go of them and then the floor is moving upward at a certain velocity. So you can see obviously why one is not going to fall any faster than the other. It's not going to matter how big they are, how massive they are, because what's really going on is this floor is moving up toward these two balls at exactly the same time. And keep in mind, say if he's going 1,000,000 miles an hour, we're out in space, there's nothing around for, trillions of miles to interfere. These things are going to be launched from his hands at that 1,000,000 miles an hour as soon as he lets go of them. But this is constantly increasing its speed, so the floor is still going to go up, 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 and it's going to catch up to these things because it's going to be going faster than that 1,000,000 miles an hour after he lets go. So these are both going to fall toward the floor at the same time because actually the floor is moving up toward them. Okay, here on Earth, I don't know if you know about this, but things always fall at exactly the same rate, long as they're not anywhere near as big as the planet. But if you have a 10-pound bowling ball and a 10-ounce steel weight, and you go up in a building 1,000 feet and drop them out the window, they are both going to fall at exactly the same speed. They're both going to land on the planet at exactly the same time. And then, of course, that won't happen with a feather because a feather will be floating in the air. The air is in between there. That's like an ocean. That's something that's resisting the fall. But if we eliminate that, don't worry about that. That's why you have a solid ball of steel here and a solid ball here. You drop them from 1,000 feet, they are going to fall at the exact same speed and land at exactly the same time. And this has been proven. Again, this is all rudimentary physics. This isn't anything new. And this is a very strong case for why there is an intimate connection between inertia and gravity. And in fact, there is. Inertia and gravity are the yin and yang of physics, as far as I'm concerned. They're the yin and yang of energy, of everything that happens. All right, so now, here's our guy out in space again. There's two rockets facing each other. These two rockets are both burning exactly the same amount of fuel. They're facing each other, obviously, but they're being separated by two steel beams. These steel beams are not allowing these things to move. So the inside of this hull is under great pressure. This is under great pressure. These steel beams are under pressure. But all that energy from the rocket ship burning, I don't know if you see that's burning at this end too, is being transformed into all this pressure, but there's no motion going on except for the fuel spitting out the back end of this thing. So the thing is, what does this guy feel here in between? Does he feel himself being pushed in that direction or that direction? Does he feel anything at all as far as gravity? Again, we're assuming we're way out in space. And the answer is no, he doesn't feel anything at all. As long as these are both burning exactly the same amount of fuel and creating the same force. So that's that guy. Love my high-tech thing I got going here. I am low-tech. I come from the past. Okay, here's number 7. This is the same thing with gravity that we just showed there. And I'm not speaking very well either. I'm kind of nervous in front of a camera. This is a huge steel sphere, solid steel. This is a huge steel sphere. These spheres we're going to imagine are so big that they have a significant gravitational force. They want to come together, but they're being held apart by these two steel columns. We're going to assume everything is identical. This is the same size as that. These are the same size. They're both perfectly round. They're all the exact same distance from the center point here. So if we imagine these things are as big as, say, the planet Earth, what would happen is there would be so much pressure in this area here that would start to heat up tremendously because of the gravity pushing this way, gravity pushing that way. And eventually they'd start to kind of melt and sploosh in together. So we're just going to imagine these things are big enough so that they're pushing on each other with a great deal of pressure. They're putting a great deal of pressure on these, but it's not creating so much heat that this thing begins to warp. It's not going to warp, we'll just arbitrarily say within 5,000 years. So here's this guy in the middle here, and the question is, what does he feel? Because these things have their own gravity. They're so big they have their own gravity. Is he feeling himself, half of them being pulled this way, and then the other half being pulled this way? Like he's split right down the middle. This half is being pulled this way, and this half is being pulled that way. And the answer to that is no, of course not. He's floating in the middle. He feels absolutely nothing. And it's exactly the same as this scenario here with the rocket ships. Everything's under pressure. The energy is being transformed into pressure. He feels nothing. Gravity and inertia act exactly the same way. There's pressure in this whole area here. If these things were too big, say if it was a brittle material, this would start to break apart and the powder would start falling in toward the middle. Or these would start to crack apart and then the whole thing would crash together. But again, we're assuming we found that window of weight, of mass, of material, where we've got as much gravity as we can produce without these things melting or falling apart for, we'll say arbitrarily, for 5,000 years. So in the middle, he feels no gravity. And again, this is rudimentary physics. This has all been proven. And now I'm just going to beat this a little bit more just to clarify things. I want to put them side by side. Here's two rocket ships. They're out in space. They're nowhere near each other. I just have them drawn this way so we can see them. There's nothing near them at all. This rocket ship is going this way. He's on a platform. He can't see the rocket ship underneath him. But there's a force pulling down this way. There's his hair. He must be a long-haired hippie. Them damn hippies. His hair is getting pulled this way. His shoelaces are getting pulled that way. This guy is on the same thing, same rocket ship, same platform. He's standing on his head. His hair is getting pulled this way. His shoelaces this way. I know this is silly, but you'll get the reason why I'm doing all this pretty soon. Same thing with two planets. They're far apart. I've just drawn them together. He's standing on this planet. Hair getting pulled this way. Shoelaces getting pulled that way. He's standing on his head on a planet. Hair getting pulled this way. Shoelaces getting pulled that way. Inertia, gravity. Inertia, gravity, it's the same. It's the same but different. It's male and female. It's yin and yang. So now we are going to show the incorrect conclusion, right? The wrong conclusion with these two things side by side. So from what we've just seen, we might think if we weren't, thinking straight, these two things are now there. They're held apart by these steel beams. Everything's under pressure. But he's cut right in half, and this half is being pulled in that direction. This half is being pulled in this direction. His hair is flying up this way toward this end. His shoelaces are flying that way toward that end. Same thing. Planets, rocket ships, same thing. He's right between two big steel spheres. They're being held apart by these poles. And the gravity from this one is pulling on this half of his body this way. The gravity on this one is pulling on this half of his body this way. His hair is getting pulled like this. His shoelaces are getting pulled like that. That's not how it works. It doesn't work that way with inertia. It doesn't work that way with gravity. Side by side. What is the correct conclusion in all this? And of course, it's what we just saw. I know I'm repeating, but it's all right. It's for a reason. Inertia, gravity, gravity, inertia. He's just floating in the middle. He's just floating in the middle. Everything's under pressure. This is under pressure. This is under pressure. All that energy is being absorbed by the pressure. All this energy of the gravity is being absorbed by the pressure. No weight, no weight. Floating in space. All right. And here's a little tidbit just to clarify all this. If you can imagine that there's another planet same size as Earth that's heading toward the Earth at 1,000,000 miles an hour. It's not going to happen, by the way. As this planet got closer and closer and closer to Earth, what would happen to you if you were standing on this side? You would start getting lighter and lighter and lighter. You would weigh less and less and less as this guy got closer and closer and closer. The ocean water would start weighing less and start kind of floating around like there was a tide. The ground would weigh less. As this thing got closer and closer, you'd start floating around, and the water would be floating around, and the dirt would be floating around, and you'd be having fun going, this is fun, I'm floating around, and then and you'd be squished. As this approached, you would weigh less and less and less. That's something to think about to clarify what we're talking about here. Okay, now this is something that NASA does, and I know a lot of people are mad at NASA. Some of NASA's stuff is fake, some of it is real. You have to be able to know the difference between what's what, and you certainly won't learn that by looking on YouTube videos, unfortunately. Alright, I'm looking for my 3x5 cards here. Okay, so what NASA does here is they have these airplanes that will go up. They'll go up, I can't remember, whatever, as high as a plane can go till there's not enough atmosphere to sustain it anymore. And then it'll come back down rapidly. It'll come down at a specific velocity and a specific angle. And when it does that, there will be no gravity inside this airplane. It will feel like there's no gravity, but if you understand what I was just showing you, you will understand there actually will be no gravity in this. So it goes up, I don't know, 80,000 feet. I don't know how high a plane can go. Then it shoots down like this, and for about 5 minutes or so, there's no gravity in here, and then they can simulate zero gravity conditions for all kinds of reasons. Whether you think it's propaganda or training for the astronaut, that's up to you. It's probably both. Uh-oh. See, now I'm wasting time here. Okay, now up in that airplane, while it's in zero gravity, you have a glass of water and you shake the water a little bit. You shake the glass, and all that water is going to come floating out of that glass, and it's going to form a bunch of drops. Alright, each drop is going to form a sphere. It's going to form a circle. And why is that? Of course, because all those trillions of molecules, they all attract each other, and they're attracting from all different distances, and they always end up forming a sphere. Right, everything has a little gravity, everything has a little inertia. Right, now down on Earth, if you have a square box, you fill it full of water, that water is going to fill out the square box. The water will fill out the shape of whatever container it's in on Earth in a gravitation. But out in space, where there's no gravity, water forms a sphere. That's what it does. That's obvious. It's known. So now we have our water drop in space, and we're going to imagine that this thing is rotating at 1 revolution per day. 1 revolution per day. That is slow. That's a slow revolution. Okay, now we're going to keep adding water to this drop and keep making it bigger and bigger and bigger and bigger, but we're going to assume that all the time it just keeps rotating at 1 revolution per day. That's half the speed of the hour hand on a clock. That's so slow you can't even see it if you were back looking at the Earth from a spaceship or whatever. Or at this drop, I mean. All right. And the thing is, no matter how big this drop gets, as long as it's only rotating at 1 revolution per day, it's going to stay together, because the more water you keep adding, it's going to add more and more gravity pulling in the outsides. So the outside might be traveling fast, but when this thing gets very big, it's really just traveling sideways at that whatever that velocity is. But the rotational spin is always 1 revolution per day. And as you add more and more water to this drop, the outside of this will be spinning faster. If you go by like how many miles an hour this is spinning, but the revolution stays the same. All right, so now this drop we've decided is the size of the Earth. Still spinning at 1 revolution per day. Here's the important thing. In the center of this drop, there is going to be no gravity. Right? Just like that guy between the rocket ships or the guy between the planets, if you were to, say, put a bubble in here made out of, hard plastic and put somebody inside that bubble, he's not getting pulled in all these different directions. He's not going to feel any gravity at all in there. Right? The molecules in there are attracting each other, but a solid object is not going to feel gravity pulling out. There's no gravity in the center, but there's maximum pressure. All this water, billions of tons of water pushing in on this is creating a lot of pressure here. On the outside, this is our drop as big as the planet Earth. There's maximum gravity, but no pressure. So this is the one of the fundamental things in the whole universe with anything that has a large mass. The center is maximum pressure, minimum gravity. The outside is maximum gravity, minimum pressure. So what's going to happen inside here at the center? This is going to be turning to steam. There's so much pressure on that, it's creating heat. It's going to be turning to steam. That steam is pushing back. The gravity is pushing this way, but little jets will be shooting out here and there, turning into whatever and then coming back. And it will look very similar to some of the films you may have seen of the sun. You see films of the sun where stuff is spitting out. That's what it is. Maximum pressure on the inside with 0 gravity. Maximum gravity on the outside with 0 pressure. And the steam wants to expand. Okay, now we're going to add solid material into our drop of water. We're going to add rocks and dirt and all kinds of crap. But keep in mind, this is always spinning just at 1 revolution per day. That is so slow. So we add a bunch of stuff to our drop of water, and it ends up looking like that. There's our big drop of water out in space, filled with a bunch of dirt and crap, and maybe there's an iron core spinning in the middle. I'm not 100% sure about that. But what's going on here? The center of this, maximum pressure, minimum gravity. The outside, maximum gravity, minimum pressure. Huge heat being created in here, which is pushing stuff out this way. That's where we get our volcanoes and stuff. Okay, now we're going to add planets around here. We're going to add a sun out here that's heating on it. Right, the gravitational influences of all these planets. I'm not going to say the planets are actually pulling on this, but they're pulling on the whole planet, but the parts of it closest to it will just weigh a little bit less. So if Mars is over here, then this part of the Earth weighs a little bit less than this part of the Earth per each cubic volume. So all these influences of all these planets pulling, pushing, the heat from the sun, the other energies from the sun, from the whole universe are acting on this. You have all that heat from the middle pushing out, Gravity influences everything. Heat, that's what's creating all our weather, our earthquakes, volcanoes, and everything else. Besides the man-made stuff that they're doing with high tech nowadays, that's a whole nother story. But anyway, so that's what's going on there, and there's a reason I'm doing all this, but it's fun to have a little bit of an idea of where our weather and everything comes from. So I hope I'm making sense. Now, here's the Earth, and here is the Moon. We all know we have tides, but the common misconception is that the Moon pulls on the tides. But we see now the Moon doesn't actually pull on this water close, and the tides follow the Moon around, right? As the Moon goes around the Earth, the tides follow the Moon. And so it seems like the Moon's pulling on the water. But what actually is going on here is the water closest to the Moon weighs less. This gravity is neutralizing the gravity closest to it. Just like our guy between the two doohickeys. Only instead of columns holding these apart, the inertia of this thing flying around is holding them apart. So this gets lighter, and then what happens is the ocean water over here and over here is heavier per each volume, for each unit of volume. Like each gallon of water here, a gallon of water here will weigh less than it does over here. And a gallon of water here will weigh less than it does over here or over here. So this heavier water pushes down and it displaces this water upwards. And that's what actually causes the tides. So now, here again my high-tech renderings. Sorry about this. This is an exaggerated version of what goes on with the tides. The water nearest the Moon weighs less for each gallon. The water out here and here weighs a little bit more. It's not very much per each unit, but there's a lot of units of water. So this pushes down here, this pushes down here, and this displaces this lighter water up this way. Because each unit weighs less. Each gallon weighs less. Each cubic foot of water weighs less. Here it is following the Moon around. Wherever it follows the Moon around, it's the same thing. The water closest is lighter. This is pushing down. This is pushing down. It displaces this water upwards or toward the moonwards. Now, if there's a piece of land here, well, that's what the tide is. This higher water is going to run into the land. It's going to stay high until the Moon gets past, and then it's going to recede back. And, this is superfluous. But yeah, so now the Moon's over here. Here's the oceans, the heavy water pushing down. Here's the light water being displaced toward the Moon. And over here where there was a tide, now the water receded back and it's back to normal. So that's how the tides work. That's how gravity works. That's how inertia works. Like I said, there is no mathematics involved in this theory because nature does not care about math. Only engineers do, and the whole purpose of this is to give engineers something to engineer. Alright, so now we're back out in space again. There's nothing around for billions of miles. Excuse me. We have our two solid steel spheres, solid steel columns. Everything's the same size, everything's the same distance from the center point. These are so big that they are creating a great deal of pressure. They're creating some heat, but not so much that they're going to start to melt. We're going to just arbitrarily decide they're going to be able to sit here for 10,000 years before the shape of this roundness gets changed appreciably, till they start to smush together. All right, so this one here, if I take this and turn it to the side, that's what I'm seeing here. It's exactly the same thing. I'm just seeing it from the side, so I can't see the other column because this is in the way. This is exactly the same thing. The columns are both there. I just have not drawn them. I cut the drawings out, but they're still there. They're all the same size, the same distance from the center point, etc., etc. And this is because of other things I'm going to show you. So now here's those same two steel spheres. Here is a pipe full of liquid. We'll say whatever temperature it is out there, this is a liquid that's being able to flow through this pipe. And we will notice that the liquid flowing through this pipe, we're going to assume this is exactly centered in all directions from the center of right here, the same distance from the columns, etc., etc. This water flowing through this pipe will not feel gravity one way or another. As it approaches, as it leaves, as it goes between the columns, as long as it's the same distance from every point that's from the center of this arrangement, the liquid will not feel any gravity one way or another. And this is also the same thing will happen to a light. If you have a laser light going through here, if it's aimed right at the center, it will not feel any gravity, it will not bend, it will not go one direction or another. Excuse me. Alright, so now we're getting to the whole point of all this, which is proof. Well, there's already been proof, but not in the way I'm showing it here. These are the same two planets. They're still held apart by the columns. Everything's perfect. Everything's under pressure. This is a 50-foot diameter pipe. This pipe is going all the way around this sphere. This pipe is lined with Teflon, so it has almost no friction. And then we have a liquid in here that is a frictionless liquid. Those kind of liquids do exist. This whole pipe is filled with these things, with this liquid all the way around. It's under a little bit of pressure. I don't mean this pressure, but like we shot it in there, kept it under a little bit of pressure so it's full. And now we're going to, what is this liquid going to do around this pipe? We're going to arbitrarily assume this is a 1,000-foot drop. This pipe here is just resting on the ground. It's just a 50-foot pipe, perfectly round. Everything's perfectly round. It's resting on the ground. This just comes out 1,000 feet. Then it's 1,000 feet above. It's being held up by whatever. And over here, and then drops 1,000 feet. Superconducting pipe full of superconducting liquid. Or I should say frictionless pipe full of frictionless liquid. What's going to happen? This 1,000-foot drop here, gravity on this side's pulling. There's no gravity over here. This liquid's going to get pulled this way. It's going to cause this thing to move. And you're going to get continuous circular motion resulting from the static energy of gravity. The static energy of gravity is being transformed into the kinetic energy of this current flowing in circles, not violating any laws of anything. And not only is this continuous circular motion caused by gravity, it's continually increasing its velocity. This thing will continually increase its velocity until it rattles apart, or until it's going so fast that there actually will be a lot of heat created in there, and then the thing will eventually rattle apart. And now here's the same thing, but I've just expanded it a little bit because we have two sides that have gravity here and only one without, so we're going to take advantage. Hope you can see that. So the same thing, there's a 1,000-foot drop. This goes up around, 1,000-foot drop, and you have continuous motion in this little figure 8 shape, or the shape of an infinite symbol. And then for any physicists out there, you're probably noticing, or I don't know if you are, but you may notice there will be some bizarre gravitational anomalies that will happen right about here, about here, about here, about here. And the rest of you, if you don't understand this, that's all right. But for the physicists, I just want to mention this. Just keep in mind that anything that happens here that would tend to impede this is going to be happening over here that's going to be tending to help it. So they're going to neutralize each other. And this is only 1,000 foot above the surface here. and the weight drops off at the square of the distance from the center. So that's not going to be, this is going to be effective 99.99% as much as this. So the total opposition to current flow through the entire thing, including these little mini event horizons, will still be less than the total force pushing this way and this way, which is causing this thing to move. So am I creating energy? No, I'm transferring energy, exchanging energy between the static energy of gravity and the kinetic energy of this current. All right, and this is probably superfluous. This is just looking at the same thing from the top view. So here's that pipe. It comes out, it goes back down, it goes underneath this one, it comes out, it goes back down, comes underneath. That's what we're looking at here. And finally, here's the last thing here. I hope I've been making sense. This is just the most efficient way of drawing this thing. Obviously, this is not a practical invention. There's no purpose of this except to prove the theory, and then there have been a couple of people that have actually done something like this physically here on Earth. But what we have here is there's our 1,000-foot waterfall, 1,000-foot fall. This goes through here. This straight pipe, as we already proved, is not going to feel any gravity at all. So we can even have both of these waters coming together in here, although there'd be turbulence and whatever. So we'll put a little turbine here and here, and another little turbine right here, so it'll absorb energy before it makes too much turbulence. These two go into a straight pipe, comes out here, and we still have our, well, no, that wouldn't work. They'd have to be separate pipes. Forget about that. These two pipes are right next to each other. So this goes into a pipe, goes this way, this comes around here, goes into the pipe right underneath or right next to it, comes up around here. We have our circular motion. We'd have to put a turbine in there some way with some little electricity pulling power out to keep this thing from constantly increasing velocity forever. So what we have here is three kinds of energy. We have kinetic energy of the current, we have the static energy of the gravity, and then the potential energy of the pressure. And to me that's just a concept, but the pressure on this, we would call that potential energy. It's similar to having a spring and you're pushing down on that spring, it's under pressure. That spring, they call it potential energy because if you let go of it, boing, it'll pop up and can cause something to move. But that's only a one-time thing. But this is a good analog to electricity now, right? The current is the current, right? That's comparable to the amps. The dynamic energy of gravity is comparable to the dynamic energy of the magnetism. And then the potential energy of pressure, that's comparable to the potential energy of the voltage. And this is actually a very close analogy, and it actually works. Now, there are two inventions that I know of that exist in the physical world that actually prove this concept. One is invented by Ken Wheeler. He's all over YouTube. His YouTube name is Theoria Apostophis. And he's got a little deal with a giant magnet and more magnets called a Hallback array, and then a cone-shaped coil, and those three things together produce enough electricity to light a little LED. The little LED is lit simply by magnetism. There's no outside power being fed to that thing whatsoever. And I mean, it doesn't look anything like this, but it proves the concept of static energy. And then there's an inventor that, he's dead now, his name was William Skinner. William Skinner, look him up on YouTube. It's a lot of fun watching that stuff. But he had a machine that actually ran on gravity. It wasn't a perpetual motion machine. He had to feed energy into it, but a lot more energy came out then was fed in. So he was ridiculed. His work never got off the ground, but all he was doing was transforming the static energy of gravity into the kinetic energy of his little his spinning weights. So, all right, that's it for that. That's video 1. There's more videos. They do get a little bit more complicated, but again, there's no math. It's all step by step, and it will be explained so anyone can understand it. Okay, thank you. Thank you very much.